Hi everyone, this is Sahir and Shara, and we did the AP Physics C3 response, Mechanics number 2 from 1994.
And also kind of obvi, but not
Alright, so here's the question. A large sphere rolls without slipping across a horizontal surface. The sphere has a constant translational speed of 10 meters per second, a mass m of 25 kilograms, and a radius r of 0.2 meters. The moment of inertia of the sphere about its center of mass is I equals 2 mr squared over 5. The sphere approaches a 25-degree incline of height 3 meters as shown above, and rolls up the incline without slipping.
Then it asks you to calculate the total kinetic energy of the sphere as it rolls along the horizontal surface, so before it hits the incline. Then B wants you to calculate the magnitude of the sphere's velocity just as it leaves the top of the incline. And then part 2 of B wants you to specify the angle at which it leaves the top of the incline. And then C is neglecting air resistance, calculate the distance from the point where the sphere leaves the incline to the point where the sphere strikes the level. And then D is a conceptual question. Suppose that instead the sphere were to roll towards the incline as stated above, but the incline was frictionless. State whether the speed of the sphere would, as it leaves the incline would be less than, equal to, or greater than the sphere calculated in D.
Alright, so part A. Calculate the total kinetic energy of the sphere as it rolls along the horizontal surface. K total is going to equal K translational plus K rotational. We know that K translational equals 1 half mv squared and K rotational equals 1 half I omega squared. We substitute in the rolling constraint and moment of inertia, and we get that what you see right here. After simplifying that a bit, we get K equals 1 half mv squared plus 1/5 mv squared, which is equal to 7 over 10 mv squared. Plugging in our values from the problem, we get that K equals 7 over 10 times 25 times 10 squared, which is equal to 1,750 joules.
Alright, part B is asking us to calculate the magnitude of the sphere's velocity after it leaves the top of the incline. So you're going to start with the change in energy, which is the energy E final minus E initial equal to work with non-conservative force, which in this case is 0. So from that, we're going to get that E initial equals E final. And we know that E initial is going to be the kinetic energy translational initial plus the kinetic energy rotational initial. And that's going to equal at the end kinetic energy translational final and plus kinetic energy rotational final plus MDH, which is the potential energy that it gains. Then we know from earlier that the total energy was 1750, so we can just set that to 1750. Then by substituting in, we know that the kinetic translational would be 1 half mv squared, the kinetic rotational would be 1 half times the moment of inertia of the sphere times, and then we substitute in the rolling constraint, and then you adding mgh. And then when you simplify, you get 7/10 mv squared plus mgh equals 1750. And then doing the math, we got v squared equals 57.1536. And that makes v 7.56 meters per second.
And part B2 asks us to specify the direction of the sphere's velocity just as it leaves the top of the incline. Realizing that there's no force other than gravity acting on it like the second it leaves the incline, the sphere is going to continue at a 25-degree angle from the horizontal, as you see in our diagram right over here. I hope that cleared it up a little. Alright, so part C says neglecting air resistance, calculate the horizontal distance from the point where the sphere leaves the incline to the point where the sphere strikes the level surface. So this is a basic projectile motion kinematics problem. First we solve for the time that it's going to hit the ground, so we use the equation y equals y naught t plus v naught t plus 1, y equals y naught plus v naught t plus 1 half gt squared. So from that, we plug in some of our values and get y equals 3 plus v sine theta t, because we have to consider the velocity only in the y direction, plus 1 half gt squared. Plugging in more variables, we get y equals 3 plus v sine theta t minus 4.9 t squared, because g is equal to negative 9.8 and 1 half of that's negative 4.9. After that, we use the quadratic formula.
Negative v plus or minus square root of v squared minus 4ac all over 2a.
Just in case you forgot. So after that, we plug in our values. So we have 7.56 for velocity, 0.42 for sine of 25, and 3 for our height, and we plug it all in, and we get either negative 0.52 or 1.16 seconds. Knowing that time can't be negative, we have to choose 1.16 seconds, and then now we solve for x. So we use the same equation except in the x direction. We use x equals x naught plus v naught t plus 1 half at squared. We know that x naught's 0, and there's no force acting in the x direction, so the acceleration is also 0. So we get x equals v naught t. We plug in for v naught, we have to plug in 7.56 times cosine theta, because now we need to look at the velocity only in the x direction. Multiply that by 1.16 seconds, and we get 7.93 meters is the distance that from the point where the sphere leaves the incline to the point where the sphere strikes the level surface.
Alright, part D asks a conceptual question that says, suppose that instead the sphere will roll to the incline as stated above, but the incline was frictionless. State whether the speed of the sphere just as it leaves the top of the incline would be less than, equal to, or greater than the speed calculated in B. So what we said basically was that the sphere as it leaves the top of the incline in this case would be less than it was in B. And this is because in the first case, the rotational energy and the translational energy both contribute to the change in gravitational potential energy. But with the frictionless surface, there's no friction to change the rotational energy, and as a result, all the change in gravitational potential energy must come from the decrease in kinetic energy. So basically, just the kinetic energy, the translational kinetic energy is contributing to this in this part. And since the gravitational potential energy is the same in this part and in part B, the ball will lose more kinetic energy and therefore its speed will be less. We done, and that's pretty Swaggie.
And I'll be Space Search. Hope this helps.